So in the lab, we always get given potato starch, but I always prefer to use a real potato because it's got some authenticity to it. So my potato's only 88 grams, so I don't know if I've got enough to do two patches. We'll find out. I'm sort of cheating a lot. I'm not doing all the grinding and the peeling and all that sort of stuff. I just throw it in a blender and just whiz it around for a minute and I'm done. All right. I do put it through a strainer. We do have some very good ones. I don't know if this one's too fine. Use that to make more char. And then just let it sit. You can see here that there's, it looks like a bit of starch. I hope it's enough, 2.5 grams. I need like 5 grams overall. So just tip that out and give it one wash and then just let it sit for another 5 minutes. So I do the wash. You can see it's way cleaner, so that comes out quite clean, and it looks quite pure. It looks very nice white sludge. Looks a lot like corn. It feels a lot like a non-Newtonian liquid, oobleck, like corn flour. And so I'll put that away and bring that into school to see if I can get that to work. So I pretty much follow the method as written here exactly, and so I'm just putting 2.5 grams of potato starch, 3 mils of, I think it's 0.1 molar. I have to go back and check what the concentrations are, and I do the full 15 minutes. I just follow it exactly as it says, which is a problem as we'll see later. So it gets gluggy and then doesn't get gluggy, and then I take a little bit of time to neutralize it. And so what I'm basically doing, you can see here the starch granules are all wrapped up, and they look quite interesting in that they have amorphous and then crystalline layers, and the crystals are parallel to the banding, which is quite interesting because year 8 is studying rocks right now, and I'm looking at a lot of rock videos at the moment. You can see that here. You can see that there's very much like a starch granule with banded layers, and then in between the white layers are parallel. So the calcium carbonate is forming crystalline circular concentric circle structures, very similar to a starch granule. So they are both chemicals, both forming crystals in a very similar way. So that's kind of cool. Rocks and chemistry are the same thing. And as you'll see from this picture here, which is quite significant because what you'll see later is I think I've hydrolyzed it too much. So I don't think you can follow the method. I think what you should do is what I told my students to do is I suspected it didn't work that well because it was hydrolyzed too much. So in the video just previous to this one, we hydrolyzed sucrose. So it would be reducing, and it hydrolyzed quite easily. This picture here sort of suggests that just heating it up or just mixing it very thoroughly is enough to break them without even the addition of acid. And so I suspect that I definitely heated it up way too long and mixed it, and it hydrolyzed far too much. And you can see and the plasticizer is meant to help. It's it being brittle, so instead of having quite strong attraction and compaction of chains, they sort of break them up, and so there's far less hydrogen bonding. There's just a little bit of hydrogen bonding between the glycerol and the chains rather than a lot of hydrogen bonding between the chains. And so when you can see the finished product here. I made it quite thin, and I sort of cooked it too high as well. I got a bit impatient as I do, and did it very quickly. The one without glycerol turned out quite nice. It's a bit too thin and couldn't get a sheet out. It's very, very thin. But you can see it's quite a nice plastic, that little tiny piece I have. It's not that brittle, but it's definitely brittle. All right. It's quite a nice plastic, actually. And the one with glycerol is just way too gooey. I think I over-hydrolyzed it so the chains wouldn't link in together. So when I realized that, I told the students as soon as it's just a little bit gooey, stop straight away. This one here maybe is still a little bit not gooey enough, maybe hydrolyzed too much. But you can see here, it's turned into quite a nice piece of plastic. It's quite flexible. And you know it's ready when it's dry to the touch, by the way. So there's a lot of factors going on in there. The different types of starches have different percentages of amylose and amylopectin. Also have the branches at different places, different ranges. And then you've got the different, you've got to really be precise with the heating and the hydrolysation. So there's a little bit of an art to that because there's so many variables. So quite good for an internal assessment, really. And so it can work quite well, but you've got to get all the factors just right. You can't hydrolyze it too much or not enough.